You've just been learning about scalar and vector fields, but now it's about time you got to learn some more calculus, because that's when things really begin to get interesting. We're going to start with the derivatives of a scalar field. But first of all, we're going to review some of the things you already know about scalar and vector fields. What I've got here is an Ordnance Survey map of the Beeston Castle area in Cheshire. You can see the contours marked on the map. There's the 1,000 metre contour, and they increase in intervals of 25 metres as you move inwards towards this central area here. Very much the sort of thing you've seen before. Right, well, let's see if we can isolate these contours. Now you're looking down on a plaster model of the area. You see the contours. Remember, they increase as you move inwards towards the central area. I wonder if you can imagine what the land area looks like there. Well, there it is. It's a more conventional picture of it. It's a hill. And you can see where the contours are close together, the hill is steep. Where the contours are less close together, the hill is flatter. Right, now let's move on to the mathematical model of this. What I've got here is the same hill, only we've made it transparent so that you can see a horizontal XY plane underneath. Now, any vector r would describe a point in the plane, and with any such point we can associate a scalar, this distance here, that is the height up to the land surface. So there we have it. And we describe this mathematically by a function h, mapping points r on the plane to heights h of r. And that's an example of a scalar field. The more general formulation of a general scalar field would look like this. It's a function r, mapping points on a plane to numbers r. According to some rule, r maps to phi of r. Well, I now want to come back and have another look at this surface, because there's more here than just a scalar field. There's a vector field as well. Watch this. I'm going to place a ball bearing on the surface and release it. You see, it moves off in a very definite direction. I'll do it again. A very definite direction. And I can do that at any point. So with every point there, we can associate a direction. And that's not all. We can also associate a magnitude, because the ball moves away faster in regions where the slope is steeper, and less fast where the slope is shallow. For example, if I put it here, it's not very steep here, it moves away rather slowly. In other words, we can associate with each point here a magnitude and a direction. And that's a vector field. Here's the general formulation. A vector field is a function mapping points on the plane to vectors according to some rule. So I think we've done rather more here than just illustrate examples of a scalar and a vector field, because we've shown a situation where a scalar field and a vector field occur together. And now Dan is going to show you some more examples of this in less familiar contexts.
The examples I've chosen are not obviously related to the one you've just seen, but mathematically they're the same. That's because they include in their description ideas of scalar and vector fields. Look at this square plate. It's made of aluminium, and it's being heated in this corner by a thermostatically controlled soldering iron. Tricky to put back. In this corner, it's being cooled by a bath of melting ice. So it's being maintained at a constant, fairly high temperature here and a low one here. So heat is flowing through the plate. Flow, now that means it's a vector quantity. It's got magnitude and it's got direction. If I choose to call this corner an origin, we can say that at a point, position vector r, we have a magnitude and direction, a vector. So vector r maps to vector h of r, the heat flow vector. Fine, so there's a vector field. There's also a scalar field. Heat flows from areas that are hot to cold, high temperature to low temperature, and in between there are all sorts of intermediate temperatures. I can measure those with a probe. The measurement will appear on the meter by the side. You can see that at this point we've got nearly 30 degrees centigrade. Now, temperature is a scalar, just a number. If I take a point, position vector r, and measure the temperature, then I can say that vector r maps to scalar t of r. We've got a scalar field. But I can do more than that. I can look for points of constant temperature. Here, for example, it takes a little while for this measuring device to settle down. Here I've got a temperature of 30 degrees. I'll make a little spot there because this probe's also got a marker on it. Let's try a little bit lower down. 30 degrees there. A bit lower down. 30 degrees again. In fact, I can join up those points. Put the probe on. Now this is very tricky to do. I'll try and move it so I join up the points and keep the meter at a steady 30 degrees centigrade. Well, that's not too bad. Let's try again. Here, it's a higher temperature. It's just over 35 degrees. Now, again, I'll try moving it very carefully. Hello, I'm wandering off a bit. No, it's about 36, 37. But again, you can see the principle. You can see I can connect up lines of constant temperature. And I can do this all over the plate and get a contour map, just like the contour map you've already seen for the Ordnance Survey. Mathematically then, they're the same, a scalar field and a vector field. Well, that's an example from heat. Let's look at another one, this time from electricity. This is a sheet of conducting material. Current is flowing from this point to this point, and you can see it on the meter at the side. We've got 10 units of current flowing. Now, in fact, this looks rather like the one you've just seen for heat flow, and mathematically, it is the same. Again, we've got a vector field, current flow. It's a flow, so it's a vector. It's got magnitude and direction. If I look at a point with position vector r, I have a magnitude and direction there, so vector r maps to vector j of r, a current vector. What about a scalar field? Well, you know from everyday examples like car batteries that current flows from high voltage to low voltage. Again, I've got a marking probe which will measure on the lower meter voltage for me. There you see I've got a fairly high voltage, sort of up towards 8 volts, and down here the voltage is much lower, not quite 2 volts. Let's try and do the same thing. Let's try and connect up points of constant voltage. Now, if I hold that on there, I've got 6 volts. I'll put the marker on, and I'll try and keep the meter on a steady 6 volts. I'm getting better at this, I think. Oh, we're a bit low there. That's not very good. That wasn't terribly good. Let's try again. It's not very easy to do. A bit higher this time, about... No, we're not marking. That's it. It's a bit higher this time, about 6.5. I think I'm doing a bit better this time. So again, you see, we can form a contour map of voltage lines, constant voltage lines. So the voltage forms a scalar field. At some point, position vector r, I have a scalar value for the voltage. That is, vector r maps to scalar v of r. So you've seen 2 examples, 3 examples if we include the Ordnance Survey, physically very different, but mathematically they're very similar. And that's not all we know. we noticed that the flow, in the case of, say, the current here, was from high voltage to low voltage. In the case of the heat, the flow was from high temperature to low temperature. So, in some way, it seems the scalar field and the vector field are connected. There appears to be some kind of a link between them.
Right. Well, I'm going to assert that the link between the scalar and the vector field is to be found in the process of differentiation. In particular, I'm going to show you a relationship between the direction of the vector field and the derivative of the scalar field. But we haven't yet defined what we mean by the derivative of a scalar field, so let's think back to block 3 for a reminder of what we mean by a derivative. Well, here it is. Given a function of one variable, the derivative, f dashed of x, is defined like this. You take the difference of the function image values at x plus h and at x, where h is an increment in x, and you divide by h, and you take the limit as h goes to 0. So, guided by that, let's see if we can, by analogy, define the derivative of a scalar field. Well, I've got a scalar field here. I've drawn some of the contours. Okay, let's take a point R in the scalar field, defined by some position vector. It's the vector R from some origin to that point. Here's the function image value, phi of R. And now we're going to give R an increment, just as we did for x, only remember that R is a vector, so the increment is going to be an increment vector. Here it is, I'll call it S. So that this point here has position vector R plus S. And here's the function image value at that point. Right, now we can define the derivative at this point R as the difference in the function image values, phi at R plus S minus phi of R, divided by the magnitude of the vector S, like this. So given a function phi, we define the derivative as the difference between phi of R plus S minus phi of R over the modulus of S. Well, we can't divide by the vector, so we divide by the modulus of S, and we take the limit as that increment goes to 0. So that seems quite straightforward enough, only there is a problem. Because you see, I chose that vector S to be in that particular direction. Well, I could have chosen the increment to be in any other direction. And it makes a difference. You get a different derivative. So we have that at a point in the scalar field, we can define not just one derivative, but an infinite number of derivatives corresponding to the different directions that one can choose for the vector S. So how do we cope with this? And what's the link between that and the vector field that we've spoken about? Well, to show you, I'm going to remind you about the direction of the vector field. You see, wherever I release the ball, it rolls down the surface along the line of steepest slope, as if seeking out the way, the shortest distance to lower contours. In other words, it moves at right angles to the contour lines. And that's the case wherever on the surface I have the ball. It always moves down at right angles to the contour lines. So let's now go back to the drawing board and see what the significance of that is for the directional derivatives. Now, I want you to remember that at every point in the scalar field, there's not just one derivative, but an infinite number of them corresponding to the different possible directions you can have. We call these derivatives directional derivatives. And I want you to think about the one directional derivative that is taken along the direction at right angles to the contour line. That is, in the direction of the increment vector S that I've put up here, at right angles to that contour. Well, what's so special about that one? To answer that question, we have to look at one of the other directional derivatives. Let's take the one defined by an increment vector at some other direction here, at an angle theta with S. And we'll choose this increment vector so that it spans the same two contour lines as before. Well, you can see how S1 and S are related. There's a right-angled triangle in here, right angle here, so that mod S1 is equal to mod S divided by cos theta. Now, what does that mean about the derivative? Well, it means that S1 replaces S in this definition, here, here, and here. But because I chose the two vectors over here to span the same two contour lines, the numerator in here will remain unchanged. What does change is the denominator. Mod S is to be replaced by mod S1. That is to say, by mod S over cos theta. So there's a cos theta factor comes up into the numerator here. So this is how the derivatives are related. Phi dashed is the directional derivative at right angles to the contour lines, and phi 1 is the directional derivative along the direction of S1. And because the value of cos theta for phi 1 will be less than 1, then this means that the directional derivative at right angles to the contour line will be the largest directional derivative that you can have. And that's important, because it means that the direction of the vector field associated with it is at right angles to the direction of the contour lines in the direction of the directional derivative of maximum magnitude. That conclusion, at least, is true in this case. Is it also true for the examples that Dan looked at?
What we now want to know is whether that special direction is the right direction for the vector fields we've seen. Let's look at the conducting sheet again. You remember, we established a scalar field by plotting out contours of constant voltage. We expect the current to flow from high voltage to low voltage, just as we expected the ball bearing to move from high contours to low contours on the hill. So the current, we think, is flowing that way through the sheet. Now, let's do the obvious thing. Let's try and interrupt that current flow. We can do that by putting a cut in the sheet. I'm going to use a knife and put a cut along here, fairly short cut, but look at the current first. We'll set the current to about 10, and then I'll put in a cut and we'll see if we can make the current drop. There it goes, it's going down. It's now gone to about, sort of just above 7.4-ish. Now, I did that by putting in a cut almost along a constant voltage contour. This time, I'll try again, but I'll put in a cut at a greater angle to the constant voltage contour. Let's mark in a cut of about the same length. We want to put one about, should we say like that? Now, let's put a cut along that line and see what happens. Watch the meter. It's set at about just below 8 units of current. Hello, it's flicking a bit. That's it, about 7.2 units of current. I'll put a cut in along here now. And you can see the meter drops, but nowhere near as much as it dropped before. Now, we want to test the idea that the current flow is along normals to the constant voltage contours. While Alan was talking to you, I prepared another sheet in which I traced out a lot of constant voltage contours. There we are. Now I'll adjust the current back up to 10 units. Now then, what I'm going to do is this. I'm going to draw in, or try to draw in, a line at right angles to the constant voltage contours. Then I'll try and put a cut along that line. Let's draw the line first. Fairly approximate, but I hope it'll be good enough for our purposes. You see, I'm trying to cross each line at right angles. Now, if our conjecture is correct, then putting in a cut along that line won't interrupt the flow of current. So the current should remain the same. So if we have a current of about 10 units, we don't expect to see it drop. Let's try and see. And we see it hasn't moved. So that demonstrates the point we wanted. The current flows normal to lines of constant voltage, and it's just the same for the heat flow. The heat flow vector at any point will be normal to a line of constant temperature along the direction of the maximum directional derivative.
Well, a number of things have come out of this. You've seen several examples where a scalar field and a vector field appear linked together. A temperature field linked with a heat flow field, a voltage field and a current field. The general picture of the link is something like this. If we have here contours of the scalar field, and if we draw lines at right angles to these contours, like this, then those lines give the direction of the vector field. And you've also seen another way of expressing this same relationship in terms of the directional derivative, defined like that. The direction of the vector field is along the lines which give the maximum value for the directional derivative. And that's very important. In fact, you're on the brink of one of the most important relationships in the whole of vector calculus. You're going to hear a lot more about that in the next program.